In a previous video, we've solved the Helmholtz equation by minimizing the total energy in the system. Now that makes sense from a physical point of view, but what we still don't have at the moment is a real mathematical proof that this approach of minimizing the energy is actually 100% equivalent to solving the Helmholtz equation directly head-on. So this is exactly what we're going to do in this video, and just to spice things up a little bit, we're also going to move from 1 dimension to 3 dimensions. So the functional we're going to be considering is a volume integral here, because we're working in 3 dimensions. And then we're going to replace the derivative of psi with the gradient of psi. So then we have gradient psi squared minus k squared psi squared, and then this whole thing integrating over the entire volume dv. And then the question is, can we find a psi which minimizes this functional, and is this equivalent to solving the Helmholtz equation? Before we do that, just drawing your attention to notation here. When I write down this thing, what I mean by that is the scalar product of the gradient of psi with itself. Now this is not equal to the slightly similar looking this notation here, which is the Laplacian, and which is something different, which is the divergence of the gradient of the function. So don't confuse these two things. Pay careful attention to where the square is and to parentheses, okay? Right, so again, we're going to find a psi which minimizes this j. So if you find a psi such that j is actually minimized, then that means, simply because we're working at an extremum, that if you're going to perturb that solution psi a little bit, then for all possible perturbations delta psi that you can think of, you will need to have the situation that the function itself, delta j, does not vary to first order. So, sorry, that j does not vary to first order, meaning that delta j is equal to 0. So our first step will be to calculate this delta j, and then impose that this is equal to 0. As a quick reminder, delta j is, of course, by definition, the j at the point psi plus delta psi. And I'm using the term point here rather vaguely, because, of course, this is a point in an infinite dimensional space. Psi is a function. So j of psi plus delta psi minus j of psi. So this is the first variation, and this thing needs to be 0 if we're working at an extremum. So pause the video here and see if you can calculate this delta j. So just a matter of plugging in the different arguments here. So first of all, we have a term where we evaluate j at psi plus delta psi. This is going to give us here then the square of the gradient of psi plus delta psi, but gradient, of course, is a linear operation, so that becomes gradient psi plus gradient delta psi. I'm going to square that, minus k squared, and then here we have psi plus delta psi squared, integrating over the volume. And then we subtract our original case, gradient psi squared minus k squared psi squared dv. Okay, let's continue working on this. Here we have 2 times a square of 2 terms. So this will give us 3 terms. This will give us another 3 terms. Let's see what happens. Let's first focus on this thing here. So the first thing we will have will be a delta psi squared. But luckily, this is exactly what we're subtracting over here. So this first term will vanish. The second term, which is a double product, will not vanish. This is going to give us 2 times, and then we have this thing here, gradient psi, gradient delta psi dv. And then finally, we have a term involving delta psi squared, but this higher order term, we're simply going to neglect that because we're working for small variations anyhow. So all the higher order terms, we're just going to throw them overboard and focus on the linear approximation here. Okay. So good news, from the 3 terms that we were afraid of, there's only 1 that is left. So that simplifies things considerably. And we can play the same thing play the same game for the second square here. because the first term will be a psi squared, which is exactly what we subtract over here. But the only thing we need to worry about is then this double product, k squared psi delta psi dv, because again, the higher order term delta psi squared, we're going to sweep that under the rug. Okay, so we've simplified the expression for delta j, but yeah, we're still very far from the Helmholtz equation, right? So the question is, how are we going to bring this expression closer to the Helmholtz equation? Well, something we can do is actually look at different vector identities and see if some of them might be useful. So for example, what we have, if we then open a small parenthesis here, it turns out that there's a certain equation that goes like this. We have the divergence of u times gradient of v, okay, with then scalar functions u and v of the three coordinates x, y, and z. This thing turns out to be equal to u, and then this thing plus gradient u scalar gradient of v. Okay. Let's see if this can help us in any way. So pause the video, and the first thing I suggest you do is verify that this thing makes sense from a dimensional point of view. So verify that each of these terms are actually scalars, as it will turn out. And then the second thing we're going to do is see if we can apply this formula to what we have over here. Here we have something involving psi's and delta psi's. Here we have something involving u's and v's. The question is, how should you map u and v to psi and delta psi? Small hint here, we're working to the Helmholtz equation. So perhaps there is a certain term in the Helmholtz equation missing, which this formula can provide us. And then what we're going to do is take this formula and integrate this over volume and see if we can use this to rearrange the terms here in our current expression for delta j. So pause the video and think about all of these different aspects. First of all, let's verify that all of the terms here are indeed scalars. So this is a vector, but the vector times a scalar is another vector. And then if we take the divergence, that's basically a scalar product giving us a scalar. Same thing over here. So the gradient will be a vector. But then if we take the scalar product with this symbolic vector, in this case, this nabla, this gives us again a number and a scalar. And then for the final term, same story, we have the scalar product of two vectors, so that's a scalar. So at least from a dimensional point of view, everything is okay. Now for u and v and psi and delta psi, remember what I said earlier here is that this thing is equal to the Laplacian of psi, so that's just a different notation here. Sorry, Laplacian of v, I was getting ahead of myself, because indeed the term we're missing here is a Laplacian of psi in the formula. So this means that if we put v equal to psi, by applying this formula, we at least get a chance of introducing the Laplacian psi into the game. So therefore, let's put v equal to psi, and that means that u should have the role of delta psi. Okay. Let's now integrate this thing over the volume as promised and see if that helps us. So now we have u, that's going to be delta psi, as we said, and then we have the gradient of psi dv. And this thing is going to be equal to, again, a volume integral of u, so that's delta psi, and then we have our long sought after Laplacian of psi dv, and then finally we have this here, which is a scalar product of gradient psi, gradient delta psi, order doesn't matter here, dv. Okay. Drawing your attention to the fact already here that what we see in this final term is exactly what we see in the first term of our expression over here. So this is exactly how we're going to transform that equation to get the Laplacian in there. So this thing here, we're going to bring that to the left-hand side because this is what we need to substitute in our first equation there. So if I do exactly that, that means that here we have gradient psi gradient delta psi dv is equal to, so this is equal to, first of all, what we had on the old left-hand side over here. Now we have a volume integral over a divergence of something. So there's, of course, the divergence theorem that will tell us that that volume integral becomes a surface integral over the boundaries of that volume of the stuff of which we were taking the divergence. So in this case, this is going to be delta psi gradient psi, okay, times ds, and I'm going to split up ds into a scalar part, ds without a vector sign, times the unit vector, which is normal to the surface that we're studying. Okay, so remember what we're doing. So we're calculating this thing from that equation. So this goes over here is equal to that guy. We apply the divergence theorem, but then we need to take this term also and bring it to the other side. This will give us a minus sign minus the volume integral of delta psi Laplacian psi dv. Okay, cool. So now we're finally in a situation where we can use this and apply this to the formula that we have over here. So our delta j, because that's exactly what we're calculating here. So let's see if I can squeeze this so that we can fit everything on the same slide. So we were calculating delta j, and we were saying that this is equal to 2 times, and then something which we've calculated to be equal to this thing over here. So let's do that. So this is then our surface integral delta psi. Now another small tidbit from vector calculus. By definition here, if you take the scalar product of the gradient times a vector in a certain direction, that will give you the directional derivative of psi in the direction, in this case the normal direction. So this, by definition, we can write as the normal derivative of psi, which I'm going to denote like this. So it's the derivative in the direction perpendicular to the surface. Okay, so then we have two scalars here, ds minus, and then the volume integral of delta psi Laplacian psi dv. Okay, so this was this first term taken care of by the stuff between parentheses here. Now, of course, we should not forget to add again the final term, which is minus 2 the volume integral of, what did we have, k squared psi d psi dv. Okay, that looks good. Right, so we've done a lot of work. The question is, are we any closer to the Helmholtz equation now? So let's see what the next step is. The next step will be, of course, demanding that delta j is equal to 0. So see what happens if you demand that delta j is equal to 0, and then try to rearrange some stuff, and then hopefully you will see the Helmholtz equation magically appear. Okay, so if this thing is equal to 0, then we can get rid of the factors 2 here, the prefactors. Let's then also collect all of the volume integrals on one hand and the surface integral on the other hand. So for the left-hand side, we have our volume integral of, and then it becomes obvious that we can factor out a delta psi for both terms. So for this guy over here, we had the delta psi of the Laplacian psi, and then over there we had k squared psi. Okay, that's excellent news, because what we have between brackets is at least the Helmholtz equation. So the Helmholtz equation is starting to make its appearance. Great. And then for the right hand side we have the surface integral of delta psi d psi dn ds. We're very close now, because, well, okay, we have our Helmholtz equation, but we have first of all some stuff on the right-hand side, and then we have some stuff around the Helmholtz equation. So how are we going to isolate the Helmholtz equation from that junk all around it? First of all, let's focus on the right-hand side. The right-hand side has everything to do with the surface, so basically the boundaries of the volume. So we're looking at the boundary conditions here. Now, there's two very popular boundary conditions. There's the Dirichlet boundary condition, which basically demands that the function at the boundary is actually 0. And there's also the Neumann boundary condition, which basically says that the derivative of the function, in our case, the normal derivative, so perpendicular to the surface, is 0. Or you can also have a mixture of both of them. But let's now look at situations where we're working with these particular boundary conditions. Then can we conclude from that that if we do that, if we're looking for functions which satisfy these boundary conditions, that then the right-hand side will be equal to 0. Now, first of all, for the case of these boundary conditions with the normal derivative, then it becomes obvious if this term here is 0, then this guy will be also 0, and then the whole thing will vanish. Same thing is true for the Dirichlet boundary conditions, but there it's a little bit more subtle because here we have psi and there we have delta psi. However, if we're looking for functions psi which are 0 on the boundary, and then if we're perturbing these solutions to look for small variations around that solution, then it also makes sense that the perturbations that we're looking for, the delta psi's, that they also are 0 at the boundary. Because otherwise, if that was not the case, then we would end up with a function that would not satisfy the boundary conditions, so therefore that would not be an admissible solution. So if we stay within the space of admissible solutions, a sensible thing to do, and if we're then looking for perturbations, then we should also have that the delta psi is equal to 0. Therefore, also in this case, we can conclude that the right-hand side related to the boundaries is equal to 0. So now we're a little bit closer. We have this thing here, and we have Laplacian psi plus k squared psi dv is equal to 0. Now, a final important realization here is that, so we're looking for functions psi which minimize our functional. So we're looking for functions psi where our delta j is equal to 0. So this is again, of course, what this equation expresses. But if we're working at a true minimum, then it should be the case that this delta j is equal to 0 is not something which holds for a particular single lucky choice of delta psi. No, this thing should be 0 for all possible variations delta psi that you can think of. So that this should be true for all possible variations delta psi. So again, if you look at a two-dimensional analog, if you have a two-dimensional minimum, which I'm sketching rather badly here, then we should have that at the minimum here. If we look at the minimum, then the variations of our function should be equal to 0 for all possible directions that you can vary in. So for all possible variations in this direction or in that direction. And the same thing is true in our infinite dimensional case. Delta j is equal to 0 for all possible variations of small perturbing functions delta psi that you can think of. And if that's the case, then the only way we can satisfy this, because delta psi is arbitrary here, is that if our function satisfies the Helmholtz equation, finally. So finally, we end up indeed that this is fully equivalent to solving the Helmholtz equation. Some pieces of terminology. This equation that rolls out of the analysis that's asking that the first variation of a certain variation expression is equal to 0. This is called the corresponding Euler-Lagrange equation of the variational form. This means that there's two ways of solving a certain problem. Either we solve the problem head-on, like this, or we solve a corresponding variational form of which our original differential equation is the Euler-Lagrange equation. And then there's another piece of terminology attached to that. If we solve it by minimizing a certain functional, then we're talking about solving the weak formulation of the problem. If we're directly solving a differential equation, the corresponding Euler-Lagrange equation of the variational form, then we're doing something in the strong formulation. So these are different terms that you might encounter in literature. But what we've shown here is that these two are equivalent, at least for the case of the 3D Helmholtz equation.